This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, I think we can start. Good afternoon, everyone. This is the last leg of the subject. We're almost done. Next week, this lecture, then next week, Wednesday, I will finish the material. I will also talk about, give it a wrap up and talk a little bit about, the final exam, etc. on Wednesday. Then on Thursday, we have the guest lecture. The colleagues from IBM, two colleagues will come and give you a really nice guest lecture. I hope you will all show up for that and benefit from it. The industry applications of machine learning and optimization as well. So our subject is also an optimization component, and optimization is being used a lot in engineering applications by itself without any machine learning component. So I was saying, it's a beautiful weather outside, but the topics that we are going to talk about are really, really nice and exciting too. So I hope you'll enjoy it. I tried to summarize really interesting, deep things in these slides, and then I will slowly go over them. So you have and these are the things that you have a chance to explore also in your workshop in a hands-on manner. We were talking about the multi-armed bandits. That is the kind of a simple form of reinforcement learning because there is no state. There is uncertainty in the environment. The agent doesn't know the environment. Still needs to learn the environment, but there is no state transitions and so on, which makes the job easier. And I gave a lengthy explanation on exploration versus exploitation trade-off, because the goal is not just to learn the environment, but also maximize the reward. So these two things need to be, compromised and traded off. And we talked about the very fundamental algorithm, epsilon greedy algorithm, that illustrates this nicely. Because on the one hand, the actions are selected in an epsilon greedy manner with probability 1 minus epsilon. Epsilon is usually a small number. You are trying to maximize your estimated reward, which is kept through the QA values, A being the action, 1 to K, the levers, so to say, of the bandit. And then with epsilon, you are doing some random actions, and then that is for learning purposes. And then this is the action selection part of the epsilon greedy algorithm. And then this is a new set of slides. I will, of course, post them the latest by Monday. And then, of course, once you do this exploitation or exploration, then you update your action value estimations to benefit from your experience, right? The idea is the more you interact with the environment, the more experience you are accumulating, and then you should use that to improve your estimates of how much each action is going to pay to me. The environment is random, otherwise it would be trivial exercise. You will try each action once, get the rewards, and then one round is enough to learn everything there is to learn. Unfortunately, life is more complicated, and in the bandit problem, you have a probability distribution of rewards for each lever, and then every time you try them, you get a different reward, maybe with the Gaussian distribution, or it could be any distribution, right? So in this case, it's all about learning those distributions. But if you spend all your time learning them, at the end of it, you will learn them very well, but you run out of time and your rewards are horrible. If you try to get greedy, you automatically get stuck in a local minimum, right? You know optimization right now. Your estimation is imperfect. You end up in a local minimum and don't get a good reward. Okay, and this epsilon, of course, someone was really nicely asking after the lecture, does it have to be constant? Not at all. As you see later, you can start with a high epsilon value, 0.9 even, explore more first, and then decrease it according to some function to 0.1 or 0.01. I mean, up to you, right? This is the simplest thing. So we start with simple. It gets complicated immediately. People improved upon this. I just want to, I'm not that, focused on the bandits, to be honest. I'm using it as I said, as a springboard to illustrate the concepts. especially this the exploration-exploitation trade-off concept, but also this action value estimation and then action selection process, which we will apply directly to the more complicated full formulation of the problem. Okay, so the one trick people came up with is optimal initial values in epsilon greedy. You can find this all in chapter 2 of Sutton and Barton book, and try to download the second edition. There is a second edition, 2018. It's in the links in the beginning of the slides. Right, so the initial, it turns out, if you follow this algorithm, the initial action value estimates, Q1A, or Q0A, if you start from 0, bring a bias to the sample average methods that we are using. And then, of course, as the experience accumulates, this bias disappears. Initial bias gets out of the way. But for methods with constant step size, the bias can be also permanent, though its effect is decreasing. So anyway, there is a bias that gives you, and maybe why shouldn't I use it to give me an initial kick? So how can I do that? Maybe there is a domain knowledge to favor some actions over others. If I go to the, a new problem, maybe somebody told me, oh, these bandits are giving better rewards, and I have this prior knowledge, right? Then if I have that, why shouldn't I use that? I can use that by giving plugging in those estimates as initial values to my Q values. Then that will make a difference, right? Because then when I use the max here, those Q values will appear a bit more. So you may have domain knowledge from beforehand like that. Or let's say you still don't know anything about the problem, but you can be optimistic about it. The trick is, it is just a trick. You can use initial estimates to simple way to encourage exploration. So if you choose the initial values high instead of 0, then that will bring some encourage initial exploration. So this technique for encouraging exploration is called optimistic initial values. So this is, again, you can have a look for deeper reading. So that's one trick. The other thing that I omitted or mentioned, but then said, let's assume for simplicity, is the non-stationary, stationarity and then non-stationarity. Remember, I just said the lever, you pull the lever, then it gives you a reward according to some probability distribution. In the stationary case, those probability distributions will be fixed. You play with it, you learn it. You do some sample averaging, as we do, and then you get a pretty good idea. But what if they slowly change? Then you're a bit more trouble, because the probability distribution also changes as you play. If they change like crazy, then you're in big trouble. But if they slowly change, then that is a non-stationary bandit problem, and it's a tracking problem. It changes, you try to catch it up, right, in the learning. The reward probabilities do change slowly over time. Then what I should do is I should start to forget my previous experiences, because the probability distribution has moved. So the idea is then using an exponentially weighted averaging. I already discussed this, right? So in the time sequencing. So what you do is, instead of in the other one, the step size was 1 over n, right? Now actually I make it a bit more general. I choose an alpha here. And if I put an alpha here, fixed alpha, notice what happens. I write it just in a straightforward way. Then it's alpha Rn plus 1 minus alpha Qn. And then I can open Qn in terms of Qn minus 1. And then write it as a long sum here. So you see this is the initial value, which is the bias. As I was saying, the bias disappears as n goes large, because alpha is less than 1 and minus 1 minus alpha is less than 1. So 1 minus alpha to the n, the effect of the initial bias will disappear. You also observe it here, by the way. And then the rewards, the older rewards are multiplied with 1 minus alpha to the n minus 1, n minus 2. As n goes large, those are also multiplied with pretty small numbers. Essentially, I'm forgetting my old rewards, but that's what I want, because the probability distribution has moved on if it's slowly changing, and the earlier samples were coming from a different probability distribution. I should really de-emphasize them and forget them to some extent. Then if I do this with alpha, then the step size alpha should satisfy these, just like the gradient algorithm. In order to converge to the right value, This is almost like a gradient algorithm. It needs to sum up to infinity, otherwise you don't go far, and then it should be square summable. So there are technical constraints. This is called square. It's square summable if it's less than infinite, and it's not. Sum is infinite. It's not summable. 1 over n satisfies. Yeah, 1 over n satisfies this, right? 1 over n squared is less than infinite, and then 1 over n goes to infinity. And you add it up. Good. So that's the exponentially weighted average to track non-stationary bandit problems. In the workshop, I gave it as a stationary, but it could have been. I could have changed it slowly, changing one of the parameters of the reward distributions. Then you will have a non-stationary environment. Does this make sense? I have at least one person who understood. How about the rest? And I don't know what the people in the watching it from home think. So that's I have this nice, forget all the rewards, exponentially yellow box coming in here, right? And then the last one, the last two I want to mention related to bandits this is the one that's been very widely used, therefore I thought I should include upper confidence bound action selection. So instead of epsilon greedy, you can also do this UCB. It is very popular if you are doing bandits. There are also links here and there. So in the epsilon greedy action selection, with probability epsilon, you do random search, random selection, right? You choose a random action. When you choose a random action in epsilon greedy, you choose one of the actions with a uniform distribution, right? Sometimes we say I randomly select. Most of the time, people mean with uniform distribution. So with epsilon probability, you choose one of the k with 1 over k probability, right? But is this the best way to do it? It turns out maybe not, right? When I do the exploration, maybe I should do this exploration business in a bit more clever way. So the thinking here is it would be better to select among the non-greedy actions whenever I'm exploring, according to their potential for actually being optimal, taking into account how close their estimates are to being maximal and uncertainties in those estimates. So I take into account this uncertainty in the estimates, and if I'm very uncertain about the lever's estimate, or action's estimate, then maybe I should spend a bit time more trying that action in order to make my estimate sharper, right? And then I do this one by one. Then in the upper confidence bound method, the actions are selected not with this epsilon 1 minus epsilon thing, but combining these two objectives. Again, we see here a kind of a dual objective, multi-objective optimization approach, because this is an optimization. It's a discrete optimization. Out of k choices, I'm choosing A, and I want to maximize my reward. The first part is the greedy part. That's the greedy objective. And the second part is the exploration objective. All right? So it's again, the dual purpose is immediately built in as a weighted sum. And C is the degree of exploration. So C is the weight. If you choose a big weight, obviously you are giving more weight to the exploration objective, and that will affect your decision. Or if C is 0, then you're greedy, on the one hand. If C is infinite, like that, with these multi-objective optimizations, it's always good to think about the two ends of it, the boundary cases. So if C is 0, you are greedy. If C is infinite, you ignore the reward maximization and you're purely exploring, according to some distribution. So anything else is in between. So what is this term? Actually, there is a lengthy derivation of it, and I'm skipping it. I could have included, but yeah, let's as I say, this is not the most important thing that I wanted to talk about. You can check again Sutton and Bartow for the lengthy derivation of this. The intuition in two bullet points of this whole thing is NTA is the number of times that action A has been selected prior to time t. That means until time t, until now, how many times have I tried this action? And then ln(t) is the time, natural logarithm of the time. And it turns out this square root term here that is weighted by C is a measure of uncertainty or variance in the estimate of A's value. So that's exactly what I said verbally. So you want to decrease the variance in your estimator, right? So you want to make your estimation a bit more precise. Remember, we have discussed this in the bias bias and uncertainty trade-offs before in machine learning. It is in a sense like that. I want to minimize the variance. And if NTA is small, then this term will be large, very simply. If I haven't tried an action, then that action will have a large value, and that will encourage me to try that action more. And if I have tried an action a lot, then this denominator will be big. Therefore, that value will be small. When I'm maximizing, then I will not try it too many times again. So that's the idea. So that's the UCB method, and I think this is part of the workshop. I ask you to try it. It is very simple. You just plug this into the algorithm here. Instead of action selection with this, you do it with the UCB, and that's it, because the action value estimation part is the same. Right? Or you can actually use this action value estimation part, but if it's not stationary, in the workshop it is stationary, so you don't need to do this. If you encounter a non-stationary problem, then all you need to do is then choose epsilon greedy or UCB for your action selection method, and then in the non-stationary case, this is a good way to choose a nice alpha and then doing tracking of your probabilities. Make sense? So kind of, as I said, there is a nice lengthy derivation. Another thing that has a nice lengthy derivation in chapter 2 of Sutton and Barto, specifically section 2.8, is these gradient bandit algorithms. As you can tell, these bandit problems have been around forever, so people have really worked on it and done a lot of analysis and algorithm development. Here, people then said, why do I just, instead of estimating these action values Qs, can I do something else? They said, people said, can we learn a numerical preference for each action and then use the combination of these preferences to make the selections? Because what do we do at the end of the day with QA is I'm maximizing argmax QA, right? I choose the A that maximizes the Q value. Here they said, let's do a preference and do it in an indirect way. And then the larger the preference, call it HA, for each action A, then the more often that action is taken, but it is not directly tying to the reward. So then how do I find this H? Because Q came directly from the rewards. Where will H come from? And at this point, first, let's look at how we use these preferences. Easiest way is using softmax. So something that has a higher preference with softmax. Softmax is, as the name indicates, doing kind of a maximization process, but it gives you a probability. It's not sharp like max. Argmax gives you one of the actions. Softmax gives you a probability. And let's call probability of choosing an action at time t equals A in terms of e to the HTA and the softmax of essentially. And all the other actions are in the denominator. That will give me a probability of choosing action A at time t, that's pi ta, right? That's my action selection strategy. And if I have this action selection strategy, now I don't have Qs, and Qs were depending on Rs. Now I need to update my Hs, right? And what's the preference update rules instead of value update rules? Then these are the preference update rules. If it is A, the action is A, then I update the action according to this. Again, in an iterative manner with an alpha step size RT minus RT bar. RT bar is the mean reward. So how much this reward deviates from the mean reward. If I'm getting better than mean reward, obviously I'm increasing the preference. If I'm getting worse than the mean reward, I'm decreasing that preference. And then I multiply it with 1 minus pi ta, so that comes from this probability. And then all other actions, I do the opposite. So if I get better reward from an action, then that preference is increased, and all other preferences are decreased with this weighting factor coming from these probabilities, softmax probabilities. So this is the bandit gradient algorithm. And then it is actually, there is again a lengthy, nice derivation relating this to stochastic gradient ascent. We are not cost minimizing, we are we are reward maximizing. So therefore it's stochastic gradient ascent, not SGD, or it's minus SGD, right? So that's the That's the idea. So just to show you that there is other possibilities. You don't have to just work with Q values. Though in most of the reinforcement learning, we'll stick with the Qs. So this is a kind of a side avenue. It also gives you a comparison of possibilities I'm estimating and then creating preferences, but then I update my preferences as well in an iterative way. Is that okay? Any questions? Oh yes, then there is that, of course, you can... this can also handle non-stationary, I think, yeah. I need to check it, but because it is the same structure as the before, yeah, you will have, depending on how you choose alpha. Also, you can change alpha as well, right? Right now, it's the fixed version, but you can also make it time dependent. You can do 1/n, or you can do, you can do all the tricks that we have done with the gradient methods in the optimization. Yeah. So this is an iterative algorithm where you iteratively updating something with a step size. In that sense, it's very analogous to what we did in the optimization. Very good question. So it also reminds me, if you know any game theory, the, imitation dynamics in evolutionary games are working similarly. Very, very independent topic, but in that case also the players choose the things that are giving more reward and shun things that are not giving as much. All right, so this is the bandits. Let's close the bandit part. Along with that, the first part of the workshop. So now you are well equipped for that. And let's go to the Markov decision processes, MDPs. And then I think you need to understand MDP in order to appreciate what's going on with the modern reinforcement learning. Therefore, this is kind of a necessary background information you should get. And you know the Markov chains, we have covered it again, and then we did even a little bit of hidden Markov models. So it's the same Markov models, but now we are going to make decisions on top of the Markov model. So let's go back to the agent-environment interaction. You know, the learner and decision maker is the agent. The thing it interacts with is the environment. And then the agent takes actions and gets the rewards. And instead of the observations now, I'm going to impose a state model here that agent also observes the state of the system. So I'm assuming some observability here, obviously. Not partially, but fully observing the state. So my action will move the environment state from one state to the other, right? So then let's look at this. Formulation-wise, we interact the agent and environment. Let us make the agent and environment interact in a sequence of discrete time steps. So it's kind of, we discretize the time, or the interaction is in a iterative sequential manner. And at each time step t, the agent receives some representation or concludes some representation of the environment state S on the basis of selected action. And one time step later, as a consequence of the action, the agent receives a numerical reward RT plus 1. Notice that now agent influences the environment. With the bandit problem, we were not influencing the environment. We were just exploring and learning the environment while increasing our reward. The environment's property, the distributions of the action levers were either predetermined or they were changing, but we had no influence on them. Now I am actually influencing the environment through my actions. So that is kind of important to realize, right? And in any type of computer game, chess game, engineering system, a robot, like you move and you influence the environment. So how do we model the environment? We use system theory, and then system theory thinking, we use the state-based representation. So the environment, my influence is moving the environment from state S to, at time t, to state st plus 1, right? So I start with maybe the environment is at state 0, agent takes action 0, at time 0 then gets a reward, which moves the environment to state 1, then the agent observes it and takes action 1, gets a second reward, then moves to that's the state, action, reward, state, action. This is the SARSA sequence, right? There's even a SARSA algorithm, but like that's that. I don't know how do you say it? Yeah, all right. That's the state action, reward state action. That's the summary of the state-based version. And now state is changing. So that's different from the bandit. It's more complicated. Still, it's a state-based representation, right? And then, if these states are probabilistically changing, then we have a Markov chain. We have a finite state Markov chain, maybe, right? So the simplest case would be a finite state version. There may be many states, millions of states, but it can be finite. In reality, you know, mathematicians like infinite things, but as engineers, we know that most things are finite. You know, or you can actually create very nice finite models for almost everything. You don't need infinities. You don't need infinitely small. You don't need infinitely big, because some things blow up at some point anyway. So you don't need the infinite. So there is always an upper bound and lower bound usually. Yeah. So that's the thing. So then let's look at it from a model-based perspective. We are talking about Markov decision processes. Actually, we have a model. If we have a model of the environment, that should tell me if I take action at state S, what reward am I going to get, and what state it is going to go next, right? That's a regular Markov chain. The difference is from the regular Markov chain is now I'm getting a reward on top of it, right? That's a regular Markov chain, but I get a reward on top. Okay, so that's the difference from the environment as an agent. When we were discussing Markov chains, even in probability, right? So the things were moving around. You were not affecting them. It was doing itself. Now you are affecting them and getting rewards. So therefore, there's this dependence. The probability was from state S to S prime, the next state. Now the probability is from S, given S, and action A, I go to S prime and get a reward. This is the key part here. This is the important part. Probability of S prime and R given S and A. Because maybe if I take another action, I will go to another state. And if I take another action, maybe I'll get a different reward. Maybe I go to the same state, but I get a different reward. All right? All possibilities are on the table. Does it make sense? This is this probability, the long version. So this is the model, right? If you have a state-based model as a Markov chain with the rewards, this is then well defined. So now this describes what the environment is doing. Right? That's good. That's good to know. It still doesn't tell me what should I do, but I can actually simulate the environment. I will come to this point. Knowing enough about the environment to simulate it and knowing what to do in that environment are two different things. That is actually a very fundamental point. Now, maybe I should make it now, because we are talking about the environment's model. Knowing the rules of the chess game and winning against Kasparov are two different things. You agree, right? Kasparov is the chess master, was the best player in the world. So knowing the rules of the chess game means you can simulate the chess game. But winning against the best player in the world requires much more than just knowing the rules of the game. It's usually easier to know the rules of the game, how the states will evolve. But that doesn't tell you how you will win against the best one. So that MDP, actually, you need to still solve that problem, right? So that is actually quite interestingly deep, maybe, now that I talk about it. Okay, we can write this in different ways, and we use the very basic probability theory with conditional probabilities. This is all about conditional probabilities. I can write it in this way. Probability, if I don't care about the rewards, only care about which state I am going to, then that would be the probability of S prime given S and A. And I can write that marginal probability by summing it over R, right? You know that. So it is important, this marginal probability business. If I sum over R, then that will give me this. And if I want to have an estimate of a reward at a given state and A, then I need to take the expectation of RT given AT minus 1 is A and ST minus 1 is S. Then that will give me the expected reward over all actions and given the previous state, right? I'm given this previous state S. Then how do I do that? I take the expectation over all R rewards and then I need to take the marginal over S prime, all of the states I'm going given the S and A. These are the arguments of the function. So given those arguments, I take the expectation over R and I take the marginal over S prime. Okay, so then that will give me this, the state action expected reward. Or actually, I can even, I don't have to take marginal over the next state. I can even take the state action next state expected reward. And then if I write that, then I give S prime as the argument as well. Then I don't need to take a marginal about it. Just take the marginal over R. And this is a conditional probability way of writing it, P of R given S, A, and S prime, right? So if you write it this way, so that's the conditional probability. So just open your probability book and just make sure that you understand these conditionals here. Making a fancy example, nice picture of Wall-E here. And then, as recycling robot, you can have the environment. The robot has the either searches or waits or recharges. There's a battery, and then actions are these, and then the states are the battery level is high or low. If my battery state is low, I go and recharge. If it's high, I go search and find the cola cans and then bring them to recycling and so on. So that's a nice example with the rewards differently defined and probabilities defined. You can make fancy models out of this whole thing. I thought these were too many formulas. You should bring some examples. So this is the one possible example. Again, I refer to Sutton and Bartow for MDP part. So that book is classic. So this is classic stuff. It's a good match. All right. Now I mentioned actually, how these things connect in the sense that, okay, I have a system, I have the environment model, I know how the system is evolving and giving me rewards based on my actions as the agent, right? I have a nice finite state model, Markov chain model of the environment, but how am I going to then, find these best actions to win, right? And then we need a few things to develop that, and this is coming deep stuff, right? So first, let's talk about the rewards. Remember rewards and then the goals, like they are not the same thing. Immediate rewards are the immediate rewards, but then I have a long-term goal So there's this reward hypothesis that we are going to use. Goals and purposes, these are the long-term things, can be formulated as a maximization of the expected value of the cumulative sum of received scalar signal called reward. So I'm I'm doing whatever I was doing actually for the bandits, in the case of bandits, I'm adding up the rewards. If it's a finite sum, and if I'm at time t, all the rewards I expect to get from time t to capital T when the episode ends, it's a finite horizon case, are just the rewards summed up, right? RT plus 1, RT plus 2, RT. So this is the return definition that I'm expecting. But if it's an infinite horizon, the thing doesn't have a stop, then if I add anything positive up, rewards are positive in this case, it will blow up, right? Or even if they are sometimes negative, there's a danger of blowing up if you get enough positive states, rewards. And we are trying to get positive rewards at the end of the day. So if I add them up simply, it will blow up. Then I should do some discounted rewarding. I put a gamma discount factor to future rewards, and then gamma for the next RT plus 2, gamma square for RT plus 3, ... So that will be then k equals 0 to infinity, gamma to the k, RT plus k, R plus 1. So because I start from 0. So I'm discounting future rewards. The thinking here is, the justification is, future rewards are so far away, I'm kind of worrying more about in the nearby future rewards. If I ask you your plans for retirement, you wouldn't have much of an idea, right? Well, I'm starting to think about retirement. It's closer to me. So you're too young to think about retirement. You're not thinking of the retirement rewards. So you're doing a gamma to the n to that. Whereas, if I ask you what do you worry about the final exam, you have a big, gamma is 1 there. And then if I ask you what about the, doing, first job, second job salary, then you do a gamma square. Gamma is less than 1. So your second job salary is not on your horizon that much, but first job salary, maybe you are thinking about it. So that's that kind of thinking. Okay, so these are the return definitions, and in both cases, let's go with the infinite horizon case, because that's kind of doesn't put a horizon business here. Only thing you need to choose is this discount factor that is less than 1. Therefore, the multiplication means future ones are discounted. It's the kind of the counterpart of doing average weighted sum, where we were doing alpha to the k for the past examples. In this case, you do the future ones are discounted. We can write it as an iterative version. Then GT will be then, as you can see, straightforward way, would be then RT plus 1 plus gamma times GT plus 1. So it's kind of an iteration, right? Because GT plus 1 is all of the rest. So you kind of combine it this way. GT equals RT plus 1 plus gamma GT1. This I'm going to use quite a bit. So this is the iteration of the return. Now, I talked about what is the best policy. What am I going to do at any given state? I don't know. In order to develop it, first I need to define a policy. And it turns out in this type of formulation, a stationary policy works. There is actually, for this setup, the stationary policy means you have a rule set that says at any state, choose this action. That would be the policy, right? Let's look at first how we are evaluating the policies. Given a policy pi, the policy's name is pi, the state value function would be then, if I follow pi, what value am I getting at state S as things progress, right? For any state, I can assign a value to that state based on what policy am I following, because it could be that I start at state S, then I take an action, I go to another state, then I take an action. How do I determine those actions? They're all given by my policy. But then I do this maybe infinite times, I sum up the rewards, and then that will give me my expected the value function. And this is exactly the thing. Expected value under that policy, GT, given the state is S, which is kind of the given is the argument of the function, makes sense, is nothing but the expected value under that policy pi, which tells me which actions to take, the sum of the discounted cost, as I defined GT, right? I just plug it in. Given state is S. And if I do this for every state, then every state is associated with a value. Good. But then that's something, but maybe I need also something else, which is the action value function. And in this case, I also bring A as a argument, just like I was doing in the bandits. So actually, under the policy pi, I can have the small q as A. That would be then given state S, and if I take an action at that point A, what would be my expected reward from that point on? So then in that case, that would be the same thing, but now conditioned on what action am I going to take at that state. All right? Because at that state, I take a certain action, it will give me a different pathway from choosing another action. So if you play chess, for example, let's make it a bit concrete. You're in the middle of the game, everything is excited, it's not clear who is winning. One action that you take, maybe you lose your queen, that has a lot of consequence, right? So actions matter. It changes the state of the system. So that's the actual value function tells you, you shouldn't lose your queen in the chess game. Right? Make sense? Yep, a little bit at least. Now we come to the principle we are going to use to solve the problem. And that is a very deep principle. And that's the dynamic programming, right? So it's one of those concepts that is very simple to state, but it's very deep. It keeps popping everywhere. And you need to relearn it every time and go deeper and deeper and understand it. It takes a while. But it's very simple to state. The dynamic programming is about simplifying a complicated problem, if possible. You cannot use dynamic programming for everything. It's not a magic bullet. By breaking it down into simple sub-problems in a recursive manner. Right? This sounds so simple to say, but it's so complicated to understand sometimes. Yeah, it took me a long while to really appreciate the dynamic programming. Maybe you're cleverer than me. It will be much easier for you, hopefully. So it ties up to this Bellman principle of optimality. Now, this is easier to a bit understand. All it says is, what does it mean breaking down into simpler sub-problems in a recursive manner? Right? That's a bit mysterious. Now we will demystify it, hopefully. Bellman's principle, in my opinion, demystifies it quite a bit. So it says an optimum policy, which is the policy like we are talking about, for example, has the property that whenever the initial state and whatever the initial state and initial decisions are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. So yeah, that's a mouthful. I like it, visually, this thing. So let's say you are trying to drive from here to your home, right? There are multiple paths. Maybe there's traffic on the Eastern Freeway as usual. Like I suffer that all the time. So, and let's say, your Google Maps or whatever navigation, your navigation says this is the best path, and let's believe it for now. We're not debating that. So if this is the best path, right, then from this point on, this is also the best path, right? And from this point on, that's also the best path. So actually, you can start from the street next to your house, and then that last step is also the best path. And you go one more step behind, then that's also the best path. So you can actually derive the best path starting from your goal and go backwards. You cannot do always this for every problem. Sometimes you don't know the goal, and so on. But like you can do back propagation like that. So that means optimal policy, like this path, is the property that the remaining decisions after the initial one have to be optimal. If I end up in this one, if this is the optimal, right, path, then from this point on, I need the remaining decisions must constitute an optimal policy regarding to the state from the first decision. So, and this is actually a matter of breaking it down into sub-problems in a recursive way, because you can do this recursively from the goal on backwards. We can actually write this mathematically, and then that's really interesting with a value function. So let's look at the Bellman equation. This is the principle, the wording, and that's the dynamic programming, ties up the principle of optimality is underlying dynamic programming. The Bellman equation is about the value function. So in this case, we have the states are x, and actions are a, like before. Beta is this discount factor. Beta was the gamma in the previous case. And I have the state transition is then x1 is this t, this counterpart of the Markov chain. But, dynamic programming is more general than Markov's. So Markov would be then the special case of this. So at any given x0 state, if I take action a0, then I will go to x1. That's what it means, right? T could be a Markov chain mapping. Now, and it could be probabilistic like that. And I start from somewhere feasible. So what does it tell me is then if I'm at x0, then if I maximize my first step, then the remaining should be then this value function in terms of x1. And if this is optimal, then if this is v star, then this should be v star at x0. The value at this point should be the best first step that will bring me to x1, and then from x1 I will have v star x1, the value, best value, optimal value for the rest of the way. This is a bit abstract. Let's go back to our problem and make it a bit more concrete, because our problem is MDP is a special case of this general formulation. Now, if I use for a finite MDP policy and value, how I derive it, the following condition that I'm going to derive holds between the value s and the value of its possible successor states. So the value function, I can write it in this way. So look at how you can write it. Value function at state s, it is what I have written, expected value gt given st equals s. That's the same. There's nothing different here. And I just plug the gt as an iterative. That's also the same from previous slide, given state is s. Now, I'm going to use the model, like the transition probabilities. This is the transition probabilities of the Markov chain, right? And then I need to take the marginals, because value is all about, under the policy pi, how do I have the value, expected reward, right? I have defined it in this way. Let's go back. This is this. So I need to sum up all the values. but sum up under the policy pi. So I'm doing that right now. So actually, if you plug it in here, if you spend a little bit quality time with this equation, you see that the pi is the policy I have imposed. That tells me, pi tells me what action to take given S. That's the first step. You need to realize this. And if I know that and take the marginal over A and then marginal over S prime and R, with the R part, then this is the part that will give me the expected value of RT, plus 1. This is that first part, plus gamma times expected value over pi, because expectation is a linear operator. I can do the sums separately. Expectation of pi gt plus 1 given st plus 1 equals s prime. And this is where I go, okay, this was s, how did it become s prime? Right? That's the only mysterious part here. We need to note that if we have this transition probability, ps prime ar given s, if I take the marginal of ar s prime of this is the same. If I sub over the a and r, actually this is the same as sum of s prime, p of s prime given s. So this is actually what's happening here is that, because that is a conditional, multiply it, then you get this. With the pi and this multiplication will give you this. That's good. Then you have a triple sum here. Then if I get rid of the double sum out of the triple sum and keep the s prime here, then this one, which is what I had here in this line, notice that expected over pi gt plus 1 given st equals s is nothing but sum over s prime, p of s prime given s. I take the expectation all over possible next steps, and then multiply it by the s prime. S prime is the next one, and then this is nothing but here what we have. The reason I'm trying to come making st plus 1 s prime the next state is, look at this. This definition is the same as this definition with one step further. Notice? So this definition is the same as that definition one step further. Actually, with all these probabilities in front and expectations, I have r plus gamma times, gamma was a constant, v pi s prime, the next state. So on the left, I have v pi s. On the right, I have v pi s prime, right? The next state. Look at the Bellman equation. Vx0 equals, under the policy, the stuff that is the immediate reward. In the Markov case, you need to take the expected reward. Therefore, there are these probabilities and expectations, plus the next value, next state's value. Vx0, Vx1. Here, v pi s prime. Then it's the same. So this is actually an instance of Bellman equation for a given policy pi. Right? That's the powerful statement. There is even a diagrammatical, because it's a bit conceptually thing, in the book, there's this diagrams. You're at state S, pi tells you which action to take. You choose one of the actions, and then based on the action you go with some probability to one of the other states, and you get some reward. So this is called the backup diagram. It's a visual help to understand what is going on. At any given state, I choose an action based on my pi policy, then that action, and then the state transition probability together tell me which state I'm going, and then I'm getting a reward, right? So in that sense, only thing we have added on top of the bandit thing is the state transitions. Without the state transitions, it's the same as the bandit thing, because every action gives me a reward. In the bandit case, in this case, every action gives me a reward, and with the transition, I go to a new state. Right? The transition probability is there, and I have the Bellman equation here. So this will help when we decide on the optimal policies. So now that I have the value function, I know how the value function changes under a given policy. Can I how am I going to derive the optimal policy? Before then, the solving this reinforcement learning task means informally finding a policy that achieves a lot of reward over the long run. I already said that in the bandit case, it's the same goal. The goal hasn't changed. I don't care which states I'm walking around as long as I maximize my reward. Or if I care about some states that I'm walking around, I should kind of put a very negative reward for going to that states. Then that will, discourage my agent going there, right? If there is an environment, like grid world, a robot, and then if there is, fire, like nearby, so then you should just give, if the states are the location of the robot, then you should give a very negative reward to the robot for going to the fire. Then it will avoid that when it tries to maximize its reward, right? So you can actually handle it like that. So for finite MDPs, then optimal state value function is simply finding a maximizing pi such that V pi s is a maximum, right? So that would be the V star s. Then pi would be the argmax of that. You will say, oh, that looks mysterious, but it's not, because we can go to the optimal actual value function, and now this is the same as the bandit case. It's the same Q function. Q star SA is nothing but maximizing pi Q pi SA. But I can tell, based on the QSA, I can choose the max A, right, greedily, and then I choose the best action. Then that will be the optimal policy. So actually, finding the optimal policy is not that mysterious. So then the Q star SA will be then expected value. If I write it, in a longer formula, plug it in, it will be then R plus, because it was from the previous decision, expected value of R plus 1 plus gamma times V star ST plus 1. So that is the, given the state is S and action is A, then this is the expected reward I'm going to get. And if I know the optimal state value function, then I can immediately write the optimal action value function that is connected to the state value function. Because state value function tells me how much reward am I going to get from that state under a policy. Action value function is also the optimal value. Optimal value tells me what is the optimal value to get from that state under the best policy, and the action value will be connected to that naturally. It is maybe not surprising to see that Bellman equations hold for these optimal value and policies and value functions. Just like we have written the iterative algorithm here, right? For a given policy, it satisfies the Bellman equation. Also, Bellman equation hold for, as you can see here, for the optimal versions of the V and QSA. So that makes sense because it's also iterative. Just like I was discussing, the optimal path should satisfy the Bellman equation. All right. I think I ran out of time, maybe. This is quite a bit of chewing, as I expected. Then I will continue next week. But then the next step is quite obvious. Once I have these fundamentals and I understand them, I will just iteratively find these optimal policies. And then doing the policy evaluation, I will do prediction. I will evaluate the policies, and then I will improve the policies, which is the policy improvement, which will bring me to policy iteration algorithm. Just like the bandits, it will have an evaluation prediction phase, and then it will have an improvement phase, action selection phase. How do I improve my policies? In this case, I'm not choosing the actions, I'm choosing the policies that dictate the actions based on your state information. So that will be next week, Wednesday. Right? I think, yeah, we ran out of time. So enjoy the workshop and do the practical version of it. And then we will continue.